What up, nerds? I'm Bryson. You can call me Bammed. And this is CTF and Cigars by Bam CTF, where I light up a cigar, I talk about CTFs, hacking, and other security related things. So, this week, I'm going to light up something I think I did this before already, but I've got a Cao. This is the Flathead V660. So, you can go back and I think I'll do a more in-depth review back then. But at any rate, it's a Connecticut broadleaf wrapper, Connecticut Habano binder, and Nicaraguan Ligero filler. Um, Overall, it's a little spicy. There's a lot of cedar. It smells great. It's got this sort of musty, earthy cedar with like a little bit of cream, little sweet, sort of aurora smell. Um, And yeah, then when you get into it, oh, the one thing I don't like about this cigar is this flat top. You can see that flat top there. It makes it really hard to cut. It always comes out uneven. Let me see if I can get this off here. All right, not great, but it did cut. Anyway, so uh, this cigar. It starts off with that sort of spicy, cedary, a little creamy, um, somewhat earthy, floral, and then it gets when you get into like the second, third, a little bit more pepper, a little more cedar, and then you got that that sweet cream as well. It gets a little sweeter as it goes, and it kind of mellows out, and it's more espresso and sugar cane at the end. It's a little tight on the draw to begin with until you get about halfway through, and then it really kind of uh, loosens up a bit. So let me get this lit, and then we'll talk about what we're going to do today, because I changed my original agenda, try to be more relevant. Yeah. All right. See, yeah, that cut was not great, and now got a bunch of tobacco falling off. Okay. So last week I started doing some malware analysis. I thought I'd start doing some of that. A little bit different than some of the things we've done before, although kind of along some of the same lines. We've done some reverse engineering on here with CrackMe's, looked at some game hacks, but we hadn't really looked at malware. So a couple weeks ago, I looked at just a sort of a basic static analysis malware room on TryHackMe. Went through that, and then last week started doing some static analysis on it was a .NET Tesla agent loader. Um, so we started going through that, and we wanted to focus on static analysis just because as we kind of go through different types of malware analysis, I thought we'd start with something easy, and .NET is pretty easy on the static analysis side because you can very simply disassemble it, and you've got your original source code. But of course, since it's so easy to disassemble like that, the malware authors try to obfuscate it, and so what we did last week was kind of look through how that obfuscation was done and then just put together a Python script to deobfuscate some of those strings. So I went ahead and finished doing that, and I will put my source code on my GitHub, which you can access through bamctf.com. So that'll be there, and I might come back to that next week. There's really not much more to do with that piece of malware because I don't actually have the payload. Because the next thing it does is it just it downloads a payload from 3 different URLs, puts them together, and then it does a little bit of deobfuscating of that as well because the payload itself is pretty heavily obfuscated. So next week I'll come back and we'll kind of look at how it does that. But since I don't actually have the payload, I thought I did, but actually had a payload for a different sample, and it didn't match up. Once I actually got into it, I realized it was the wrong payload. So and of course the C2 site that it was downloading the second stage from is offline now. So oh well, missed that. But I'll go ahead and talk through it next week. Anyway. But this week, I thought I'd do something a little more relevant to the immediate news cycle, and we'll talk about DearCry. So If you're in this industry at all, you've probably heard of these recent Microsoft Exchange vulnerabilities that has been keeping all of us busy for almost 2 weeks now. Um, so there were, if you haven't heard of them, then maybe hopefully that means that you don't manage your own on-premise Exchange server, and so you haven't had to worry about it. If you do and you haven't heard of this, then you're probably going to have a bad time, um, because essentially just about every on-premises Exchange server that wasn't patched right away got some sort of compromise. For the most part, the bad actors were just dropping web shells, and so there were just web shells all over the place. You could get on as early as the beginning of this week. You could look up vulnerable. If you through Shodan, you could get a list of all the servers that are hosting the vulnerable version of Exchange, and it was still like 60,000. There was still like 15,000 in the U.S. Um, anyway, it's getting better, but there's still a lot of unpatched systems out there. And then the other thing is once things, if you've already been compromised, they've dropped a web shell on your system. Some other people are coming in and reusing those web shells. And patching doesn't remove the web shells. You still got to clean up after you patch. So all that is to mention DearCry, which is a new ransomware variant that just showed up a couple days ago, and it's the most of the news articles you read are a bit misleading. It's not actually using the vulnerabilities that I mentioned, which are collectively being referred to as ProxyLogon. So it's not actually actively exploiting that. According to sources, I haven't actually seen it exploit any of our customers that we've had data or access to yet. But from what other people have told me, what it's doing is it's just reusing web shells that have previously been dropped by some organizations or some bad actors, and for the most part, it's just specific web shells that have statically defined names. So we've seen a number of different types of shells being dropped. A lot of it's China Chopper. There's been some PowerShell payloads and Mimikatz and stuff like that. But originally, the original sort of disclosure about this 0-day that was being used in the wild, there was a list of shells and file names that they were seeing used, and then so there was a number of like statically defined shells file names that were being used across multiple organizations. And so then the next thing we saw was different organizations started using randomly generated names, and some even were like changing those names of those statically defined things. But then with DearCry, what we're actually seeing it do is using those already existing web shells that have those statically defined names back from when this all began. So there's a limited subset of people that this will affect. There's still way more than there should be, because it has to be somebody who's already been compromised and has one of these specific web shells on them. But that being said, don't think just because you've patched your systems that you're safe. You still got to find those shells, because in this particular case, even if your system is patched, if the web shell's already there, they can still use that to upload and run this ransomware. And yeah, I don't remember if I mentioned that DearCry is ransomware, but yeah, it is. So I had some people ask, and I thought I would give it a try. We're going to take a look at DearCry and do a little bit of reverse engineering. It's actually not very complicated, so this may not take very long. But let's switch to my analysis box. All right, so I mentioned this before. What I'm using for analysis, I'm using something called Flare VM. So this is it's just a PowerShell script, really. So you just set up a Windows VM and run this PowerShell script, and it's something developed by FireEye. It just downloads a ton of different tools and puts them all in one place. Makes it really easy to use, and then I just uploaded it to AWS, and what I do is I'll launch a new instance, do the analysis of whatever it is that I'm analyzing, and then when I'm done, I can just kill it. I do have the security group set up so that the only network connection is inbound RDP from my specific IP address, and then there's no outbound activity with a couple of holes poked in for S3 so I can transfer files to and from the instance. Now, this may not be the best way to do this. I mean, it seems to work pretty well for me. Other ways you can, if you want to spend some time doing malware analysis, never do it directly on your computer. Generally, the way it's done is through something like this, usually VPS or a VM. Sorry, not a VPS. A virtual machine. You know, you can use VirtualBox, VMware, whatever. And what you want to do is get all your tools installed, get everything set up, and then take a snapshot, and then you can do your malware analysis, and then restore back to that previous snapshot when you've done. That's important. Is you need to be able to save the state of the system and then restore it when that you're done, because there's a good chance that the malware is going to screw some things up. Remember, malware is dangerous. So you've got to be extra careful. Also, you want to disable any network activity that isn't absolutely necessary for a number of reasons. One is you don't want the malware to spread on your network, because some malware will do that. You also don't necessarily want to be spreading malware to other people on the internet, or you don't want your home computer all of a sudden attacking other servers trying to make exploits. A lot of ISPs will detect that and send you like a cease and desist or something. Or, I mean, I think most of them will say, hey, you've got malware and work with you. But at any rate, you don't want to do that. So just disable the network access. You also don't want to, reveal to the bad guys where you are, what your IP address is. There's a number of reasons why you should practice good SecOps and keep all of your, essentially don't allow your VM to do anything you don't absolutely want it to do, and it 100% has your permission. So it should not be sending a single packet that you do not approve of. All right, now that I'm done with my rant for now, let's take a look at this malware sample. All right, so first we're gonna open this up in PE Studio just to get a little bit of info about the binary file here. All right, so we see it was written in C++. It's executable. Not terribly high entropy, so that's something to keep an eye on. Gives you a clue about whether or not it might be packed or compressed or obfuscated in some way. One of the first things you often do when looking at malware or reversing anything is, look at strings. And so if they pack it, it's going to obfuscate those strings and you can't really see them until you unpack it. Also, anyway, continuing. Let's see if there's anything else interesting in here. It all looks pretty straightforward. Where is, oh, I'm waiting on that strings list to load. That's what I'm waiting on. There are a couple of interesting strings in here, so I thought we'd take a look at those when this loads. Okay, well, while that's loading. Oh, now it pulls up, of course. Go away. Okay, so here's the string. So there's a lot of, kind of interesting things here. Of course, I've been working on this system all day, and then the minute I start recording, things start acting up. I wonder if I ran the malware and left it running. I don't see any. Let's see, any .crypt files? Nope. Okay. So it's just P Studios being a pain. Okay, well, there we go. Now it seems to be working. All right, so yeah, interesting things. We can see it's calling crypto. I mean, we already know this is ransomware, but if we didn't, we can see it's calling several cryptographic things, AES, RSA, and it's actually loading OpenSSL. So that is something that's mildly interesting. A lot of not a lot, but some ransomware they actually use like Microsoft's APIs, and so there's a crypt encrypt and a crypt decrypt function that you're looking for to figure out what algorithm they're using and where the keys are and all that stuff. This one doesn't use that function. Instead, it's using OpenSSL instead of the Microsoft crypt API. So it will look a little bit different. Anyway, we see all these different, this stuff getting loaded. Let's see. Some other, a lot of crypto stuff. This is an interesting, and when we load it in some debuggers and stuff, it'll actually mention this. This is a link to the PDB file that's used for debugging. So if we were debugging this, we could pull that out. So that's there. I think this is the public RSA key. So that's there. So that's how this is being encrypted. It's using a public key that's embedded in the in the binary itself. It will then use that to encrypt it, and then it makes an MD5 sum of that key. And then when you get the ransom note, it tells you to include that MD5 with the email that you send to the people responsible for this, and they'll use that to match the MD5 of the public key to the private key that they have, which they will send you hopefully after you pay them in order to decrypt. So all right, so these are just some of the imports. I do see this is debugger present, although when I was disassembling it, it never got called. Let's see what else we got. More crypto stuff. If we keep going, we'll find the note that gets left. We do see there's some AES stuff going on. Oh, what was that? G hash for x86. All right, well, at some point there's a ransom node in here. Although when we actually get to our analysis, we'll see it in memory, assuming I get my breakpoints right. Here's some more stuff. Different variables, different. Yeah, nothing too interesting there. A lot of crypto stuff. Okay, well, scrolling through lists of text isn't that interesting. Oh, here we go. Here's something interesting though. Yeah, the list of file extensions that it will encrypt. So that's there too. Okay, let's just dive in. Let's pull up x32 debug and open this file. All right, so let's check our breakpoints. So I already set a bunch of breakpoints, probably more than we need to here, but at first it's going to break on the entry point, and that's just default. So when you load it, it loads all the things that does all the things in the background that need to happen in order for a new process to be generated. I'm not exactly sure what that looks like on Windows. I know in Linux, you basically you fork the process, you create a copy of it, and then you rewrite the headers. But I assume it's something similar in Windows. At any rate, you set up the new process, and then that's where the first, once it actually starts entering or begins loading the program itself, that's when the first breakpoint is, and that's the system breakpoint here. And then when it actually gets into user code, that's going to be the entry point, and then we've got a breakpoint there. That's just the default breakpoints that X32 debug will put. So there's the system loading the object, and then once it's all loaded, when it actually starts running in user code. Okay, and then I put a breakpoints on like a bunch of crypto functions here. We've got a breakpoint on this start service CTRL dispatcher. So if you actually were pull this apart in a disassembler and looking in like IDA or something, you would see that that's one of the basically right when main starts, its first function that gets called. So that's something we're going to break on. Take a look at what that does. More crypto things, certificate things, dealing with strings, virtual allocate. So if it was packed and so anytime we need to assign a group of or some memory for use, we're going to call it virtual alloc. We can use that to track different things that might be happening. Is debugger present? So that's checking. That's like anti-debug technology. There's malware authors typically don't want people to be able to disassemble it too easily, so they'll check for a debugger, and if there is, then the idea is to have it crash and not work. It's usually pretty easy to get around, but you'll still see that. So we're going to watch it create files. If it deletes any files, get info on drives, read files, write files, and then it actually opened a console when we launched it. So this is running from a console, so we've got that open as well. So we're going to, break on that as well. All right, hopefully I didn't miss anything, so we don't miss important stuff that happens here. But let's go ahead and start. So we're going to start by, running to user code. That should give us, so that puts us at our breakpoint, our entry breakpoint. And then let's just run it. So I'm going to do F9. So F9 is just run, and it'll basically just run till we hit a breakpoint. All right, so we hit a breakpoint on get file type. So what is get file type? So this is something that if especially if you're new to this, RTFM, Google it. Figure out what these functions are being called and how they work, so you can understand kind of the flow of things. So these are Microsoft APIs. So this is how we're interacting with the operating system. So let's see. Let me switch to. Yeah, there we go. Get file type. So there's the Microsoft documentation. The function get file type, it passes a handle, and then it returns let's see. There we go. Returns one of these codes depending on the file type. So we can look at what is passed to it and what's returned to figure out what the file types are. So switching back to RDP, there we go. Okay, now we can see right here. So what's being passed, in this case, it's in EAX. So this is one of the registers. This is a general purpose register. So a lot of functions or things, when they get called, they'll put variables in, EAX, EBX, ECX, EDX, that then get parsed when the function's called. So according to documentation we read, the argument is the handle. Let's take a look at this process. So I'm gonna open process hacker, and let's find our process here. Okay, there it is. Let's take a look at the handles. So that handle was 9C. Here we go. So this is a device con DRV. Essentially, this is the handle for the console that we open. Probably not everybody thinks this way, but for me, I think of it like a file descriptor in Linux. That's more relatable for me. But yeah, when you open a file or it's still a file here. It's why it's given a file handle. there's different types of files, and a console can itself be a file. So that's open. It's got a file handle. And then if we keep running, so what I'm going to do is I'm going to do a control F9. That's going to run until we get to a return. So now, right now, we're actually outside of user code and basically in the DLL that this function was imported from. So we don't want to step through all that. There's going to be a lot of machine level things happening that are going to be kind of more difficult. They don't help us any. We just need to see what gets returned. So we'll do a control F9. It'll jump through all that till we get to the return. So this is basically when this function is ending and it's going to return a value. We'll do a F7 to step into, and here's what we get returned, a 2. So that's also the return value, and is EAX for this function. And if we go back to the documentation, we can see that 2 is a character file, typically an LPT or a console. Anyway, just what we would expect to see because the file handle was a console. All right, let's just continue. We don't need to keep looking at that. It basically does the same thing again for the different handles for that console. Okay, now we've got a new function that's being called, and this time we broke on start service control dispatcher. So remember, I mentioned that was one of the first things that the main function called. So up to this point, we were just accessing the console, reading it. I didn't break on all that stuff, but yeah, it's just reading environmental variables, reading the arguments passed on the console, parsing through those. That's what we've skipped over here. And then it jumps into this. So we're going to start service control dispatcher. So I guess we should Google that. Where's my browser? There's my browser. All right, start service control dispatcher. Okay, so this connects the main thread of a service process to the service control manager, which causes the thread to be the service control dispatcher for the calling process. So we're starting something as a service, essentially. So we're creating the dispatcher that handles that, basically the control interface with the service control manager. And back to the analysis box. And we can see here the name of the service that it's trying to start, which is called MS Update. So it's basically registering a new service called MS Update, which is just this ransomware. All right, I'm gonna run that, and you can see here I got access denied because I'm probably not running with the right permissions to do this. So that didn't work, but it won't stop it. It'll keep doing its thing. So let's we'll F9 again, and now we've got another breakpoint. And if I didn't mention, F9 is just continue, which will just run until it hits a breakpoint. Okay, so get drive type A. Let's just go back to our documentation again. Determines whether the disk is removable, fixed, CD-ROM, RAM, or network drive. Okay, so we just pass the root path name, and then we return one of these numbers depending on the type of drive. Pretty straightforward. Let's take a look at what's being passed here. Okay, so we can see in this case EDX is C. So we're trying to get the drive type for drive C. So we will do a control F9 to execute until a return is hit. There's our return. We'll do an F8, and we can see that this is drive type. Wait, did I forget to? No, okay. drive type 3. So we see there an EAX was returned 3, which if we go back to the documentation, we see that a 3 is a fixed drive. So this is the hard disk, as we would expect it to be. So this all's making sense. Now let's, okay, then we do a comparison. So we're comparing 5, the actual number 5, to EAX. So why are we doing that? Well, again, let's go back to documentation. And you can see that 5 is a CD-ROM drive. So what we're doing here is we're going through and enumerating all the drives and checking to see if one of them is a CD-ROM. And then if it's equal, we'll jump here. If not, we'll continue. And let's see, we get the, if we continue, we get the, yeah, the address for this object where EAX is at, and then we push that to the top of the, or sorry, we load this into EAX, and then push that, because we're going to push EAX to the top of the stack, and then we'll call our instruction pointer. So essentially, this is going to, it's adding it to the top of the stack, so we're adding a list of drives to scan. And if it's a CD-ROM drive, then we go somewhere else. We basically just skip it, and then we start going through and enumerating more drives. So if it's looking for all drives except for CD-ROMs in order to search for files and then encrypt them. That's what I'm getting at. Okay, so we can continue here. We kind of know what's going on with this. So now we've got, yeah, just some more of this. Okay, so now we've got create file A. So now we're accessing files on the system. Let's go back to our documentation. Let's see what create file A says. Okay, so we can use it to open a file or an I/O device. We've got, let's see, we've got file names, access mode, share mode, etc. And I think it just returns 1 or a 0 for success or failure, if I remember right. Sorry, the return value is an open handle to the file. Okay, right. And then it returns an invalid handle value if it can't open it. Okay, okay. Always RTFM. All right, so we've got a file, and we can see actually here at the top of the stack. So EAX in this case is just a pointer that's pointing to the top of the stack here. So this is what we're looking for. So we're trying to open this file. You know, I must have missed a breakpoint. There's another breakpoint for finding files, and yeah, I must not have set that one. But at any rate, we can actually see if I set that. Let me go find it. We can find it next time around. But we can actually watch the system looking through. Okay, so I went to symbols and I did a search right here, and then I'm doing an F2 to set this breakpoint, just so you guys can follow along with keyboard shortcuts and stuff I'm using. Anyway, so yeah, we can actually watch it enumerating through the drive. So this thing's jumped into finding files to encrypt immediately. Just wanted to point that out. Like we just launched, it tried to start a service, and then we're going through. We found all the drives that we want to encrypt files on, and now it's actually finding all the files and going to start encrypting them. Okay, so create file A is again, that was according to the documentation. This is just really to open a file. So this is the file we're going to open. We'll do a Control F9 to go to the breakpoint, and a And we can actually see here what's being returned. Let's go back and look at our file handles, and there we go. We can see the return value, which is an EAX, is the handle for this file that's been opened. So, and again, the handle is basically just a shortcut in order to access that area of memory where that thing is loaded. Don't tell any computer science teachers that was my definition, because that's not really great. But anyway, all right. So we return. There it is. We've got our file handle, and how do I want to do this? Let's just start stepping through this. And I'm doing a F8 to step over so we don't go into each function unless it's something that I want to go into. I don't want to miss the interesting bits here. And I feel like I'm missing some important breakpoints. Okay. All right, we can see it's doing something with the file in memory. We've got okay, I should have been watching. Got the file name in the stack. Okay, all right, so now we're calling create file W. Set a breakpoint there for next time. All right, so let's see what create file W does. All right, so we'll look this up. Microsoft documentation. Creates or opens a file. Function returns a handle, blah, blah, blah. Okay, so we're still just getting the file open, getting information about it. Also, we'll return a file handle. I think we're still looking at the same file here, so it should be the same handle, but let's see. We will step into that. Let's run to return. Yeah, so 15C, that's the same file handle. Okay, let's keep stepping through. Ah, crap, I missed that function call. It's fine. Yeah, I know this is thrilling stuff, just stepping through assembly. I don't want to miss what I'm looking for here. I think we're still a ways though. Let's just continue. Let's see where we go. Okay, now we're going to read the file, and let's see. We're reading the file. We should probably look that up as well. Let's get that documentation. I stepped through that too quick, I bet. Let's switch to Microsoft documentation. Exciting stuff. Okay, so yeah, read file, it reads the file. Yeah, pretty straightforward there. We pass it to file handle. Yeah, I already stepped over that. I should have pointed that out, the actual file handle that was being read, but it was that same 15C. And then this is going to return. Okay, this is what I was thinking of earlier. This is a 0 or 1, a success or a failure. It returns a non-zero number on success and a 0 on a fail. All right, so we've read the data. Let's see, see if we can find what it read. Nope, it's not there. All right, well we'll find it when we get to it. Let's keep stepping. probably should have taken some notes. Oh well. I'm going to just continue. Okay, where are we breaking? Oh, string copy. I don't think I need that. Actually, no. Yeah. Okay. So we're copying some data here. Is what's going on. We can see it here in memory. Okay. So yeah, we're loading this for this variable. I didn't see where we were copying it to, but all right. So we've done a string copy. We've got this in memory here. Okay, it's at the top of the stack. So we've loaded the file name to the top of the stack. Essentially, it looks like there's a pointer here. Let's follow that. Okay, but that's just the pointer to this address. All right, let's run that. We're breaking on strcat. Okay, let's continue that. All right, so we've loaded some things in the memory here in the stack. We've got, file name, and then we've got this .crypt. So that .crypt is the extension that gets added to the file. And what we'll see, if we keep stepping through this, what we'll see is this being moved around, and the string gets copied, and then the .crypt gets added to the end of it. But that happens slowly, byte by byte. I don't know if we want to sit here and just watch that happen, but eventually we will end up with, okay, we're going to create a new file. Now that we've done all that stuff, we've got the file name, create a new file. Okay, we're still opening that. We're still finishing up with the original file, but in a second here, there we go. You can see now we've got this new file name. And I think this, if I didn't step out of the way, I think 160 is going to be the file handler for that. I may have stepped too far. Nope, it is. Okay, yeah. So we can see the file handle for the .crypt file. So now we've got a new file created, and let's see if it's here. So we're going to go to the recycle bin. There's the directory, and okay, so that file wasn't there a second ago. Now we have it, so it's starting to encrypt this desktop.ini. So far, all it's done is it's just read the original file. It's got it in memory. It's got the file name. It's created a new file name. All that stuff with the string copy and all that stuff was just to add the .crypt to the end of the file. And now it's called create file W. So it's opened a file. It didn't exist, so it had to create a new file, which is empty because we haven't actually encrypted anything and loaded any data into it yet. I mean, to be honest, there's really not much more this thing does. It finds the files and it encrypts them. I mean, that's pretty much it. So let's return. Let's see, where are we? I think that the thing that I missed is where it actually compares the file name to the list of extensions. And that's what I was trying to look for as I was stepping through, and I must have stepped over it somewhere. But you can see when you get to that point, and I had it yesterday, but actually I might have a screenshot of that. Let me see. Just a .crypt generates random data. Okay, let me, since I'm not finding it in memory right now, because I'm getting a little, well, because I didn't sleep last night because it was, D&D night. That's my usual excuse every other week. Let's see. I should be able to. I might have been on the wrong screen for a while. I apologize for that. Hopefully, I was describing things well enough you caught it. But let's look at this PowerPoint where I just took some screenshots and threw them into a PowerPoint yesterday. There we go. So there's a screenshot I got from yesterday. So what we see here, I'll zoom in just a bit. We can see that there is a there's an offset inside the executable here being called. And when we were looking, you remember when we were looking at strings, we saw this list of file extensions. Basically, this just actually calls that specific offset, pulls out that data, and then pushes it to the top of the stack. And then I just followed that memory address so we can actually see it here in the memory dump. This is when you actually go to that address and that offset. This is what you see. It's just a list of the extensions, and yeah, those are all the files that it encrypts. It does bypass the Windows directory, bypasses app data, and there was one other I think that it bypasses. At any rate, it leaves enough unencrypted files for the your programs to actually run, or at least your computer will work. You just all of your data essentially that they're trying to keep you from, because wiping a machine and reinstalling software is no big deal. That's easy to do, but you need your data. Okay, let's see if we can find where some actual encryption is going on. So we've created a file. Let me double check, make sure I'm on the right screen. Yes, I am. Okay. Okay, so we've got our file. We've got our, and in case you missed it before, this is where we are. We're in this recycle bin directory. It's taking desktop.ini. So it was doing a find, and it really is just going through the entire hard drive alphabetically. And $recycle bin, that symbol is above A when you're alphabetizing, or at least when this find function does. So this is the first thing that hits. And yeah, so it finds desktop.ini, and then I was starting to encrypt it. So it created an empty file, and that's basically where we are now. So next, where are we breaking? Okay, so now we are breaking on crypt acquire context W. So this is where we start getting to encryption. And let's look that up. So crypt acquire context W. There we go. So what does this do? All right. First of all, this API is deprecated. What if this is the right documentation? Well, we'll run with it. I don't think it actually calls wincrypt.h, so this may not be the right one. Let me look real quick. Look at our symbols. It calls crypt32, but I don't see wincrypt. I think. All right, so the documentation may be a little bit out of date, but I think for the most part it tells us what we need. So Yeah, so it requires a handle to a particular key container within a particular cryptographic service. The return handle is used to in calls to crypt API functions that use the selected CSP or cryptographic service provider. All right, so we're setting up our keys for our cryptographic functions. So what do we pass? So we pass a pointer to the CSP. We've got our name of the container, string that contains the name of the CSP to use, the type, a provider to acquire, flags, and then we get these various return values. So let's see what we have in our code here. Yeah, there's data. So going back to the documentation, that first variable there on the stack is a pointer. Okay, that makes sense. That looks like a pointer. Then we've got a name for our container, a null terminated string that contains the name of the CSP. Yeah, this doesn't exactly line up. This may not be the right API. But hey, we'll just run with it. Because I'm getting tired. So it's essentially we're just setting up the cryptographic function, for our cryptography stuff. All right, which screen are you guys seeing now? Okay, yeah, you're on the right screen. Yeah, I apologize earlier. I'm just now seeing some of the comments y'all are leaving that I was on the wrong screen before. So sorry about that. I will try to pay more attention. So let's run. All right, so we're calling cryptgen random, which I mean seems pretty obvious what that does. I would think. Let's see, cryptgen random. Okay, we'll switch to documentation just so we can, actually look at that. Fills a buffer with cryptographically random bytes. Yeah, so that's what you expect it to do. It generates random data. So we've got a handle where it's going to be stored, the length, and the buffer here that's going to receive the data. Okay. What does it return? Okay, it's just error functions or whatever. Okay. All right, so let's see what this does when we call it. Okay, let me go back to that documentation because I already forgot what it was set. Okay, so the first thing is the handle of the okay, that's the CSP. Got it. Yeah, and then the length, and then the buffer. Okay. So let's see what the handle is. All right, we haven't actually called the function yet. Let's step a little bit. Okay. Let's look at our handles again. Here we go. We can see, yeah, we're accessing the service manager here. We're accessing the registry keys. Here we go. We've got these devices, 188, 198. So these were opened by the cryptographic stuff. I don't see them here in our stack. Yeah, I think I am looking at some outdated documentation, so it's a little bit off. We should have a buffer here somewhere, and I believe this is it. So we should get random data here if I'm right. If not, then nothing will happen. There we go. It just filled our buffer up here with random data. So we've got that buffer. We're going to return that. And then let's see if we can figure out what it's calling here for the encryption. I know this is something when I was looking at it earlier, I think I stepped over too quickly and I missed it. I mean, I know from what other people said, we're using AES and RSA, and we've already seen the RSA key in the file itself. Okay. So I'm not as great at reading crypto functions in memory as I need to be. I need to practice some more. But I think right here we're actually doing the encrypting. So we're going to jump into some loops. Let's see. We were taking EBP. That's the base pointer, which was pointing to. Yeah, I should have checked before I kept stepping, but it would have been pointing to our data here, and then it was. No, sorry, it was it's taking the stack pointer. Yeah, it was loading it into EBP here. Okay, it's moving ESP to a pointer of EBP minus 18, EBP minus 20, etc. So we're getting all that set up, and then we're doing some comparisons here, checking to see if ESI plus 74 is 11111. And then yeah, we're stepping through. This is actually in the built-in crypto library. So one of the things that where this didn't. It's not using the Microsoft Crypt API, so we can't just look for the call to crypt encrypt. It looks like they've actually compiled it with Open SSL libraries, built in, and it's calling those functions. It's not actually. Well, let me double check that. Never mind. No, it is. It's sorry. It's accessing the Open SSL libraries and doing stuff. So these weren't actually listed in the original imports when we opened it. So it's actually something that got opened as we went. Here we go. This is what I've been looking for. Crypt encrypt. Okay, that's the piece that I was missing earlier. Now let's just run it. And we've stopped on a breakpoint. Okay, there's nothing interesting here. Keep going. All right, so we're doing crypt acquire context again. More crypt acquire context. And now we're reading a file. Okay, so now we're doing a read file. That nope. Let's see where these all go. Or actually, let's just step through this, and we can get. Oh, it just returned to 1. Oh, we're just loading DLLs. Okay. There we go. Now we're going to start getting interesting. So we're going to start writing our file here. Let me make sure nothing's written to it yet. Okay, it's still empty. still an empty file. Now we're going to start writing to it. And you can already see here on the stack, we've got DearCry that we're calling. All right, so we've returned. I don't think it's actually written yet. Nope, not yet. Oh, nope, there we go. It did write. Yeah, so once it finished write file, it wrote all this stuff to our file there. Okay, but I don't think it's done. It hasn't written dear on the top. So that was our encrypted data. Calling read file again. Write file again. Now let's see what our file looks like. Still looks the same. Okay. I wonder if I stepped over something. At any rate, yeah, there should be a DearCry header there. Let's just keep running. So let's return. We'll return that. So we're calling delete file now. Okay, now we're calling find next, and you can kind of see the pattern, the search pattern here as we look through this. So it's basically finished with that. If we go back and look in that directory, the original file's gone, and we just have the .crypt file. So now we're finding the next file. Let's keep stepping through this. All right, so we've moved into a new directory. We can see it here. And let's just look at this. Okay, yeah, that's the same thing. We're still looking. And we found a new file. So it's using create file as to open that file and access it. So we're still doing that. And it's going to just kind of repeat this process. So, yeah. Opening the file, checking the file type, creating a new file, which is going to be the .crypt file. Getting that file type, reading it. And let's see. Actually, okay, sorry, we're in a new directory now. Which directory are we in? Let's see. S15. Yeah, I think that's the one. All right, so getting set up to do the same thing, create file. I'm still trying to find where it calls crypt encrypt. I just want to confirm where it defines the encryption type. Yeah, we've got our .crypt file now. Gonna read, write. Did we write yet? Yeah, we've already written. All right, well, yeah, I missed it again. Let's clean up some of our breakpoints and just call those the one crypto function. And then we'll start over. Because that's like the one thing that I want to grab that I haven't gotten yet. So we got crypt encrypt. That should be it. I don't think we're generating a key, but let's go ahead and add a breakpoint there. Anything here that might be interesting? All right, let's just restart. We'll just run it and see if we ever call crypt encrypt. Step into this. Yeah, here we go. I think that's where we are now. Well, I don't know. I need to read more on the OpenSSL documentation, I think is what this is coming down to figure out what's going on here. So, anyway, to summarize what we've seen, what did we see? All right, you open the file, it tries to start that service MS update. Then it immediately starts enumerating drives, looking for a CD-ROM drive. Then it goes through and finds files, compares them to that list of file extensions, and from there, if it matches, it will encrypt it. It's using a public RSA key. I believe from what we've seen and what other people are saying, it's using some it's using RSA and AES. I didn't find that exactly, but I'll keep looking into it. I may follow up when I read up on the OpenSSL documentation more and find that. So I'll check on that and I'll let you know. But yeah, RSA and AES, that's what some other experts have said. So that's probably what we're doing. Anyway, then it's just, it's adding that DearCry and then the encrypted data, as you can see here, to a .crypt file, and then it deletes the original file. And then it just does that through all the drives. And that's it. And then it drops a note. And you know what? I didn't find, I think I skipped over the note, but let me see. I've got that here in my screenshots I took yesterday. Yep. Let's switch over to that so you can see what the note looks like. Nope, wrong window. There it is. Okay, so this is where you can see the note. Let me zoom in a little bit here. Again, it's just finding an offset in the binary itself where the readme.txt exists, and you can see it's here. Here's readme.txt. Yeah, there's some other strings here. This is where we get the MS update, and then here's basically the note. So your file's been encrypted. If you want to decrypt, please contact us. That's a represents a string in C, and then what we get passed to it would be that MD5 sum of the public key. Send us the hash. There's an RSA, and then there's also a it's not in this screenshot, but there's also a couple of email addresses. I didn't really want to give those out unless you I mean, I think they're out there, but anyway, that's pretty much it. And yeah, I know this was kind of a random stream of consciousness. So I didn't exactly plan out what I was doing. Like I did look through yesterday. I took some screenshots. There were a couple things I hadn't found yet, and then I just kind of rolled with it this morning after staying up all night playing D&D. So that's my life. But yeah, there's nothing special for Exchange here. It just finds files and encrypts them. And like I said, they're not even using the exploit. They're just using existing web shells that are already there. So that's it. Yeah, I did get a new microphone. I hope it's Hope it sounds okay. I noticed my snowball that I had it for a few years, and I probably blown a lot of smoke into it. So it was starting to get a little bit of staticky. So I went ahead and replaced it with the Yeti. I think it's doing okay so far. We'll see how well it handles the smoke. I know that's not great for it, but this is the format I chose to do, and I'll have to live with the consequences of my decisions. Okay, well, yeah, I think that's all for today. Next week, I'm going to spend some more time looking this week, and I'll kind of confirm the crypto algorithm. So I'll go back and touch on those, and then I will also kind of finish up the Tesla agent loader that I was looking at last week. So again, we were just doing static analysis on that. So somebody had asked me why I was, writing a Python script to the code to strings rather than just running it and pulling them from memory, and it's because I specifically wanted to do this as static analysis. Definitely doing the dynamic way would be much simpler, especially in .NET, because you can very easily see the source code, set the breakpoint in the actual C# in this case source code, and then once it hits that breakpoint, you can just read the value in memory rather than having to decode it yourself. But I just thought it was worthwhile to actually go through the decoding, seeing how it works, and writing your own decoder. I haven't yet, but I'm gonna put that source code for the decoder that I wrote in Python and that I kind of went over last week. I'm gonna put that up on my GitHub, which you can access through my website, bamctf.com. And I think that will do it for this week. We do connect through my employer, ConnectWise. We do have a CTF coming up in late April. When we get all those details ironed out and we're ready to tell everybody, I'll give you some more details. Just know there is one coming up, and we will keep working on all this exchange stuff because it's not over. There's still going to be a lot to deal with. Not to mention, there's a couple more RCEs released earlier this week on Microsoft DNS. So plus all the F5 stuff. So there's a lot of major vulnerabilities lately. It's a busy time to be alive. May you live in interesting times. And next time you find yourself get stuck, don't forget to try harder, don't panic, and always RTFM. Thanks for listening to my random stream of consciousness. Goodbye.
It's a madman, the battle fight.